let us first go through the case of so-called undamped oscillations, meaning that there is no friction force and oscillations are going to continue forever. Well, so we have this spring, and suppose that we put a weight on it. So then, of course, the weight pulls down, and the spring is strained a little bit. So suppose that the length of the original spring is L small, and the additional displacement under the object's weight is L capital. So let us look at the forces. Right, so there is one force that acts on the since now everything is balanced, the spring is not moving. It means that the sum of all forces is 0, and the forces are, there is the hook law, which is the spring's force acting on the weight, and there is the weight of the object itself, which pulls it down, right? So the spring pulls it up, and the gravitational force pulls it down. And balancing the two forces, we get that Gm minus Kl is 0, or alternatively, K equals Gm over L. This is important because the spring constant cannot really be directly observed. So that's a way to measure the spring constant. So you need to put a weight on it and see how much the weight strains the spring, and the displacement gives you the way to calculate the spring's constant. Okay, now suppose that we do this. Let me show you. There are 3 animations here. All of them are nice, and I suggest that you view all of them, but that's probably the nicest of all. Right? So suppose that, let me do this first. Right, so that's so now I put an object. Its mass is 100 gram. So it stressed my spring by an extra 10 centimeters. And now suppose that I do not have any friction force, then I can pull it a little bit further, and then it starts oscillating. This is what is going on here. So let u of t be, so again, let L be the original length of the spring. L capital is the extra displacement when everything is in balance. So L small plus L capital is kind of the equilibrium state, is the origin. And let u of t be the extra displacement. So if we pull it further, and then u of t, of course, it's going to start oscillating, and now this extra displacement is a function of time. And then we can write down Newton's second law, and by canceling mg minus kl, so from the previous slide, mg equals kl, so mg minus kl is just 0. The resulting equation is therefore mu double prime plus ku is 0, right? And substituting k that we also found in the previous slide, we can transform this equation. Right, so there are 2 versions of the same equation, so the undamped spring equation. So notice that the one with k is probably not so good because k cannot be directly observed. So of course, if you know k, then it doesn't matter, but usually you do not know k. So you can, you know g, the acceleration of gravity, you know L, which is the directly observed, so how much the weight displaces the string. But k itself is not directly observed. All right, so the characteristic equation here has 2 complex roots, and the general solution. Notice that the real part is 0, so the roots are purely imaginary. It means that, and the real part goes into the exponent in the general solution. So e to the power 0 is going to be 1, so which means that there is no exponent at all. It's just the combination of cosine and sine. Right, so that's the general solution. And of course, if you prefer, you can, instead of square root of g over L, you could write down square root of k over m. Same thing. So here is an example of a specific word problem that something like this you might get on your midterm test or your application exercises. So the first thing to notice is that there are centimeters here. Right? So when we want to solve it, of course, it is better to convert everything to the same units, and since we know the acceleration of gravity in terms of meters per second squared, so it's better to convert centimeters to meters. And so we see that the mass is additionally displaced. Okay, so a mass of 1 kg stretches a spring 9.8 centimeters. So this is big L. So the additional displacement is 5 centimeters, is the initial value of u. So we displace it first and then let it go, and then it oscillates. So the words displaced and released, they kind of do not imply that we try to push it anything further. So we just release. So, and release means that the initial speed is 0. So that's why I wrote that u prime of 0 is 0. And then we just write down the specific constants, mix everything together, and that's our solution. So with a given initial condition, we can find the constants, and hence the final answer is this 0.05 cosine of 10t. A little remark that the general solution, which is a combination of cosine and sine, is very often written in the form, I don't remember how, there is a name for this formula, okay, I just don't know. But this is, you can just Google it up, and I suggest that you try to figure out how these R, delta, and omega, how these are expressed in terms of, what is delta, by the way? I think it's omega. I know that there is delta too. So there is omega, omega is given, so that there is delta. So delta is the phase. I think omega is the, R is the amplitude, omega is frequency. Yeah. Well, anyway, I suggest that you try to figure it out, or you Google it up and share via the online discussion board. The reason why it is more convenient to write down the general solution in this form is because it becomes easier to solve the initial value problems. Okay, and finally, if you want to play with graphs, see how these parameters, the amplitude, the natural frequency, the phase, all these parameters, how they affect the period of the motion and the graph of the function u as versus t, you can click here. So I prepared a little animation for you. So, and for example, if you increase L, right, so the original displacement, then you see that the period of the motion becomes bigger, right? So if you decrease g, then the period of the motion becomes bigger. So if changing delta means that it's kind of moving left or right. That's the phase, and the amplitude is just this, how far it goes.